Isaac Newton remains a towering figure whose genius continues to resonate within the annals of science. His contributions, both visible and esoteric, not only provided the quantitative foundations for gravitational theory and calculus, but also ventured deeply into realms of symbolism, alchemy, and the metaphysical underpinnings of natural philosophy. In this video, we explore the duality of Newton's persona. As a groundbreaking scientist responsible for revolutionizing our understanding of the cosmos, and as a clandestine alchemist whose rigorous investigations into chemistry challenged the boundaries of contemporary intellectual inquiry. This script dissects his early influences, his technical achievements in optics, mechanics, and mathematics, and his profound yet often overlooked commitments in alchemical research. With meticulous attention to advanced topics and number-driven analysis, our discussion unpacks the minutiae of gravitational attraction, spectral composition, and the intricate calculus that underpinned his paradigm-shifting breakthroughs. For an expert-level audience, we will unravel the layered complexities of Newton's manuscripts and the quantitative rigor embedded in his scientific formulations. Prepare now for an in-depth examination that challenges conventional narratives. Isaac Newton was born on December 25, 1642, in Woolsthorpe by Colsterworth, a modest hamlet that belied the monumental legacy to come. Emerging into a world steeped in religious reform and scientific ferment, Newton's early life was marked by both personal challenges and profound intellectual curiosity. Raised in an environment where classical learning and natural philosophy intersected, he was exposed to the works of ancient mathematicians and the early voices of modern scientific thought. Newton's education at the King's School in Grantham and later at Trinity College, Cambridge, provided him with the advanced mathematical tools and rigorous experimental techniques that set him apart from his peers. As England navigated political upheaval and the religious discord of the 17th century, the seeds of the scientific revolution were taking root, nourished by emerging ideas about natural law and the structure of the universe. Newton absorbed these trends, integrating them with his own innovative approach. His early writings reveal a precocious mind that questioned entrenched doctrines while pursuing empirical evidence with relentless determination. Despite economic hardships and disruptions, his academic journey was characterized by exceptional accomplishments in mathematics and philosophy that anticipated future breakthroughs. His work in geometry and early experiments in optics further underscored the blend of intuitive conjecture with quantitative analysis. Throughout these years, Newton not only assimilated prevailing doctrines, but also experimented with innovative apparatus and puzzles that defied conventional wisdom. These early experiences crystallized his intellectual foundation, preparing him to challenge and redefine established scientific paradigms. Newton's scientific contributions stand as enduring pillars in the edifice of modern science. His formulation of the universal law of gravitation marked a decisive moment in scientific thought, uniting terrestrial phenomena with the motions of celestial bodies. By articulating that every mass exerts an attractive force on every other mass, diminishing inversely with the square of the distance between them, Newton provided the first quantitative description of gravitational attraction. This groundbreaking insight not only explained the elliptical orbits of the planets, but also offered predictive power unparalleled in earlier theories. Beyond gravity, Newton revolutionized the field of optics. His demonstration that white light is composed of a spectrum of colors fundamentally altered the understanding of light and color. Through experiments with prisms and novel lenses, he revealed that the phenomenon of color was an intrinsic property of light itself, rather than merely a product of the medium through which light travels. Newton's meticulous quantitative analyses in optics laid the foundation for a more rigorous, mathematically driven approach to experimental science. In mathematics, Newton's creation of calculus represented a paradigm shift in the methods available for understanding change and motion. Independently of Leibniz, his development of analytic techniques enabled the solution of complex differential problems that had confounded earlier scholars. Calculus, as conceived by Newton, became an indispensable tool not only in the physical sciences, but also in engineering and economics, marking a revolutionary transformation in mathematical analysis. Newton's work in mechanics, encapsulated in his seminal work, The Principia, showcased his ability to synthesize observation with rigorous mathematical formalism. His laws of motion, particularly the second law, which quantitatively relates force, mass, and acceleration, remain central to modern engineering and physics. Moreover, his method of systematic experimentation and logical deduction influenced generations of scientists, embedding a tradition of empirical validation in scientific inquiry. His approach was far ahead of its time, blending theoretical construct with experimental verification. Newton's insights into the behavior of fluids, the stability of planetary systems, and the propagation of light are testaments to his multidisciplinary genius. The precision with which he described and mathematically formalized natural phenomena enabled his contemporaries and successors to expand upon his theories with ever-increasing sophistication, thereby catalyzing the scientific revolution. Moreover, Newton's ability to quantify phenomena extended to his early work on heat and thermodynamics, albeit in rudimentary forms. His influence persists today in the forms of mathematical modeling, experimental physics, and the enduring quest to comprehend the natural laws of the universe. In essence, Newton's body of work not only transformed the framework of his own era, but also provided the bedrock upon which modern scientific inquiry is constructed. Newton's integrative approach merged mathematical abstraction with tangible experimentation. This synthesis enabled him to decipher complex natural laws and set the stage for future innovations. His methodologies, characterized by rigorous quantification and inquiry, continue to inspire research and technological breakthroughs in multiple fields. The legacy of his scientific contributions remains a testament to the power of human intellect harnessed by investigation. While Isaac Newton is predominantly celebrated for his groundbreaking contributions to physics and mathematics, an equally compelling and more obscure chapter of his intellectual pursuits lies in his extensive studies of alchemy, or chemistry, as it was known in his time. Over the span of nearly 3 decades, Newton devoted close to 1 million words to exploring alchemical theory and practice. These writings, frequently interwoven with elaborate annotations, reveal an investigator who was as meticulous in his experimental alchemy as he was in the formulation of his classical laws. Newton's alchemical manuscripts blend empirical trial with metaphysical exploration, merging symbolic imagery with quantitative observation to protect the craft secrets of ancient traditions. Deeply embedded in the context of early modern science, alchemical texts of Newton's era often employed allegory, wordplay, and coded symbolism to obfuscate their deeper meanings. Newton's engagement with these texts was not a mere academic exercise. It was a pursuit that bordered on the mystical, yet remained grounded in his characteristic analytical rigor. In this corpus, one encounters chemical processes described with mathematical precision, theories of matter and transformation that prefigure modern chemistry, and reflections on the correspondence between natural phenomena and divine order. The meticulous cataloging and annotation of these alchemical manuscripts, carried out by Newton himself and later preserved by institutions such as Cambridge University, underscore the complex interplay between art and science in his work. Even as some portions of his alchemical writings were dispersed and sold at auctions, sparking interest among both scholars and collectors, key segments were reassembled by figures such as John Maynard Keynes, who recognized the profound significance of these texts. Their survival, now partially available through projects like The Chemistry of Isaac Newton, allows contemporary experts to delve into the intricate layers of allegory, symbolism, and early experimental science. Newton's alchemical studies have provided modern researchers with rich, quantitative insight into the transitional period between medieval mysticism and early modern scientific inquiry. Far from being a diversion, his alchemical research exemplifies his relentless search for universal principles underpinning both physical reality and metaphysical order. By interlacing technical experiments with elaborate symbolic narratives, Newton not only sought to uncover material transformations, but also to elucidate the fundamental harmony of nature. In this dual pursuit, he exemplified the synthesis of empirical observation with a more esoteric quest for transcendental truth. These extensive alchemical endeavors reflect Newton's capacity to bridge quantitative precision with creative exploration. His experiments in sublimation, crystallization, and transmutation were conducted with the same rigor as his studies in celestial mechanics. Through obscure symbols and coded language, he sought to transform base metals and the fundamental principles of natural philosophy, anticipating ideas that would later emerge in modern chemistry with zeal. The apple incident remains one of the most iconic episodes in the story of scientific discovery, though it is often shrouded in myth and selective embellishment. According to accounts provided by contemporaries such as William Stukeley and John Conduit, the simple observation of an apple's descent spurred Newton to ponder why objects fall directly toward Earth's center. This seemingly mundane occurrence became emblematic of the universal principles governing both terrestrial and celestial motion. While some critics dismiss the narrative as a myth, the historical records indicate that Newton himself recalled the moment with clarity, emphasizing the natural consistency exhibited by falling objects. For experts, the apple is not merely a quaint anecdote, but a symbol of Newton's capacity to extract profound generalizations from everyday observations. The geometrical and mathematical reasoning that followed this observation ultimately led to the formulation of the inverse square law of gravitation. During a contemplative stroll in the garden, Newton questioned the nature of gravitational attraction, hypothesizing that the same force pulling the apple to the ground extended far beyond, governing the moon's orbit and the motions of the planets. This insight not only unified the mechanics of earthly phenomena with those of heavenly bodies, but also underscored the power of methodical inquiry in uncovering universal laws. Thus, the apple incident encapsulates the essence of Newton's approach, a harmonious blend of empirical observation, rigorous mathematical analysis, and creative insight. It invites experts to reconsider the interplay between apparent simplicity and underlying complexity in scientific phenomena, challenging established narratives and inspiring novel interpretations. Subsequent analysis by experts has revealed that the apple's descent, when examined through the lens of advanced kinematics and gravitational modeling, embodies the elegance of Newton's deductive reasoning. Isaac Newton's legacy extends far beyond his immediate scientific achievements, permeating the very fabric of Western intellectual history. Revered by contemporaries and successive generations alike, Newton has been hailed as the quintessential genius whose work underpins the foundations of modern physics and mathematics. Prominent scholars such as Joseph Louis Lagrange and James Jeans have extolled his intellectual prowess, and his Principia Mathematica is often cited as the greatest work of theoretical physics ever composed. Such accolades reflect not only the transformative nature of his discoveries, but also the enduring influence of his methodological approach, which combined rigorous experimentation with profound mathematical insight. This monumental impact on scientific thought is further evidenced by the numerous monuments, statues, and commemorative artifacts that celebrate Newton's contributions. For instance, his ornate monument in Westminster Abbey stands as a testament to his lasting imprint on society. Similarly, public polls and scholarly surveys have consistently ranked Newton among the greatest scientists of all time, a recognition that underscores his unparalleled influence. His image on banknotes and his memorialization in literature and art serve to continually remind us of the breadth and depth of his contributions. Newton's methods have also been foundational in shaping subsequent scientific inquiry and technological progress. His systematic exploration of natural phenomena set a benchmark for empirical investigation that influenced figures ranging from Michael Faraday to Albert Einstein. In contemporary academic discourse, his work is continually re-examined and reinterpreted, further cementing his status as a paradigmatic figure in the evolution of scientific thought. The mathematical and experimental techniques he developed remain integral to modern scientific practices, ensuring that his contributions continue to inspire innovation and debate. Beyond science, Newton's legacy infiltrates cultural and political spheres. Enlightenment thinkers, such as John Locke and Adam Smith, drew upon Newtonian principles to formulate new approaches to understanding society, economics, and governance. His vision of a universe governed by immutable natural laws resonated deeply with the revolutionary ideals of the Enlightenment, instilling a belief in rationality and progress that persists in modern thought. Contemporary scholars often point to Newton's fusion of empirical evidence with creative reasoning as a model for interdisciplinary inquiry, merging the arts with the sciences in ways that challenge conventional boundaries. Ultimately, Newton's legacy is not confined to the annals of scientific textbooks. It lives on as a vibrant part of our cultural heritage. The convergence of his analytical rigor, inventive spirit, and profound insights continues to inspire current and future generations across diverse fields of inquiry and innovation. Newton's seminal work has been meticulously analyzed by experts through quantitative models that underscore the precision of his experiments and calculations. His pioneering techniques in mathematical modeling, experimental design, and theoretical synthesis continue to serve as a benchmark in cutting-edge research. Newton's revolutionary ideas catalyzed the Enlightenment, providing a framework that extended well beyond the confines of natural science. His rigorous methodology, grounded in empirical observation and mathematical precision, inspired philosophers and economists alike to reimagine the principles of governance, society, and human rights. Figures such as Locke and Voltaire adopted Newtonian natural laws as metaphors for social order and individual liberty. In the realm of economics, Newton's quantitative approach paralleled the emerging analytical methods that later formed the basis of classical economics. His influence compelled a re-evaluation of the world, fostering a spirit of inquiry that questioned tradition and championed progress. As Enlightenment thinkers embraced his ideas, they laid the groundwork for modern political and economic theory, embedding the rational principles of science deeply into the fabric of Western thought. Newton's influence reshaped not only scientific discourse, but also philosophical and political thought. His integration of empirical observation with logical reasoning offered a model for rational inquiry that spurred debates on human nature and society. By inspiring seminal thinkers to adopt Newtonian methods, his work laid critical foundations for modern political theory and economic analysis, cementing his legacy as a catalyst for the Enlightenment's transformative spirit and enduring intellectual influence. In summary, Isaac Newton's life embodies a synthesis of rigorous scientific investigation and esoteric inquiry that continues to captivate experts worldwide. His dual legacy, spanning definitive breakthroughs in gravity, optics, and calculus, and the profound depths of alchemical research, challenges both traditional and modern paradigms. Through carefully quantified experiments and imaginative exploration, Newton forged a path that redefined natural philosophy forever. As we reflect on his enduring impact, we celebrate a mind whose innovations have left an indelible mark on science and culture, inviting future generations to further unravel the mysteries of the universe. Newton's genius endures as a beacon of discovery.